Welcome to another AQA AS chemistry video. Today I'm going to be doing infrared spectroscopy. Infrared spectroscopy happens across the entire exam, well not entire exam, but for organic chemistry, it's one of the things that you need to be able to understand, and it's very simple to understand once you get the hang of it. But you need to be able to understand it in order to answer questions on identifying compounds, and especially identifying functional groups. So infrared spectroscopy is used to identify certain bonds within a compound, meaning it's pretty useful in distinguishing between different functional groups. So firstly, I need to actually get in the exam, you'll get a booklet like this. So alongside your actual paper, you'll get a booklet like this, and it's your data booklet, right? So, and it contains, it's not going to be in this order. I only did it in this order to make it match. This would be on the last page. You'll use this for when you do the DNA section, which is in year 2, organic. But you have obviously your periodic table. Your periodic table will have your MR value. So your AR values are going to be, you have to use them to the point. So in GCSE you could get away with just saying 56, like the AR for the atomic mass for iron would be 56, but in A level it has to be 55.8, for example. So that's not one of the things here. I just want to mention that quickly. And then the last section, this is going to be your data sheet. So one of the sheets is going to be in year 2. You cover something called NMR, and I think, do you cover it in year 1? I'll double check if you need to know that in year 1, but it definitely there's 2 types of ways of identifying. Well, there's technically 3, but you only need to know for data sheet wise. Obviously, there's mass spectroscopy, which is the last one I did, and then the ones that they give you values for, which is NMR. There's 2 types of NMR, but I do not have to worry about HA1 NMR and carbon-13 NMR. I'm focusing on infrared spectra, and these are the values for each type of bond. They fall into this category. So if you get a spectrum or a peak in these ranges, you know what type of bond it had. So if there's a peak between 750 to 1100, you know that is a carbon-carbon single bond. And the same applies to everything else with certain varieties, such as broad spectrums for alcohols, and I'll cover that as well. But this is something they give you this in the exam. And over time, like, I already know that for alcohol it's 3,230 to 3,550. I just know that, but this comes up in the exam and you need to understand what it is, and it's very easy to understand. But I'll go through the video now, and I'll stop waffling. So, bonds in infrared. Infrared radiation is absorbed by any polar bond. So non-polar bonds don't absorb radiation, or they absorb it less, I should say. So as you see here, NH bond is the most polar bond out of all of them, and hence why it would absorb the most of that infrared radiation. Whereas a carbon-carbon, as we know before, as I said in many other videos, the carbon-carbon covalent bond is the least polar bond. It's not very non-polar. Of course, there's some polarity there, but in essence, it's very non-polar, and hence why it would absorb the least amount of that infrared radiation. Polar bonds only absorb radiation of a specific frequency, hence why you can identify them. So bonds have a specific frequency in which they get absorbed, and the absorbed infrared radiation marks the bonds. So the absorbed infrared radiation makes the bonds vibrate and stretch. Well, my chemistry teacher always told me that it makes the bond, when they absorb this infrared radiation, it causes the bonds to stretch and vibrate, and the frequency absorbed is specific to each bond. Different bonds in different places can have different frequencies. For example, an alcohol OH is different to a carboxylic acid OH. So you can have an OH, for example, if you have the same type of bond but for a different type of compound, because the OH is on a different, it's in a different area on the molecule, and it can cause that bond to vibrate in a different way. So for example, an OH on an alcohol will have a broad spectrum between 3,230 to 3,550, whereas an OH in a carboxylic acid, I think it still has a broad spectrum. I think it's a roughly broad spectrum, but it would be in the range of 2500 to 3000 is much more distinct. So some of these kind of cross over, but that one definitely, you're able to tell that one apart. Anyway, so I mean, it's other thing, I'll move on to that. Anyway, common frequency. So the frequency is normally reported as a wave number, and a wave number is just 1 over lambda, where lambda just represents the wavelength. Why did I say frequency? That's wrong. Oh. That should be wavelength. My bad. Done. Great. So I have obviously a couple of images here interpreting the spectra. So the section from 1500 to 500, it's 7 centimeters to the power of -1. Except for it's 1 over lambda, 1 over the wavelength, and that's called the fingerprint region. So this region is from 150 to, so from 1500. So from 500, should be the other way around. From 500 to 1500 generally is the fingerprint region. And this is very specific to, it's not always like, but it's like, yeah. But like this generally from here to here, you kind of, this probably isn't the best example to show it, but it's usually a load of spikes up in, the other example show it? Yeah, it's more like this, right? And, or more like there, that region there. And this is specific to each type of compound. So if you want to, every compound has a specific fingerprint region, and you can use a database to find that specific fingerprint region to identify a compound. So in the exam, they'll ask you, why is this compound, if they ask you, there's a question passed where it asked you, how is this compound different to this compound? And you say this, you'll have a question where it say, okay, it has, if you did the iris spectra, it would have a broad peak around this region here, between these two values here for this, and that means that it had this bond, and had a broad spectrum, had this bond, whereas this compound had a peak here. But one thing that everyone always forgets to mention, and it's always the mark, and you always get a mark for it, is that you can mention, obviously you get the majority of the marks for mentioning the differences in the peaks. That's what the majority of marks, identifying, saying, oh, there's a spectrum here, and then that means it's an NH bond, whereas this one has a peak here, whatever. But whatever, everyone always forgets to say the fingerprint region. You get a mark, the fingerprint region is specific to that compound only. So if you're talking about which compound is, if you're talking about what the difference is between the compounds in the IR spectra, you always have to mention, always remember to mention, they have different fingerprint regions. That's always a mark in the exam. And so, yeah. So there are large databases of fingerprint regions. So, sorry, did I mention that? Yeah, sorry, I forgot to say. This is usually small, full of small peaks, and it's specific to any molecule. There are large databases of fingerprint regions, and you can search for a match to identify your compound. If you don't have access to the database, most helpful bonds are outside of this region. So not everyone's gonna, you're not gonna know every single fingerprint region. So the best way to identify them is by their broad peaks and the peaks and how broad they are, and where they peak, and relating them to the general infrared absorption data that you're given in the exam. For example, the previous slide, so the previous image I showed up there, acetic acid, which has a peak of 3000 because of the carboxylic OH, and are at 1720 because of the carbonyl bond. So if we look here, acetic acid, so it has the, yeah, that is acetic acid. So it has a broad spectrum of between 2500 to 3000. So 2500, it's not going to be exact, but you can see generally from 2500 to 3000, that's where the general peak is, and that means that is a carboxylic acid OH, and then there'll be one around, in this example here, is between 1,680 to 700 to 1,750, and that represents the carbon bond here, and that's exactly how you say it in the exam. You just say there's a peak between 2,500 to 3,000. If you haven't got the mark yet, you have to say that means that there's a carboxylic OH or an acid OH. That's one mark, I believe, and then you get another mark for saying there's another peak between these two values here, and then that represents, or in this case, 1,680 to 1750, and that represents, centimeters per -1, and then that represents a carbon bond, and that's where you get your marks. Then you have to say, out of everything there, that means that this must be a so and so whatever compound, and that's how you identify your compound, right? So, absorption of infrared radiation and global warming. So, absorption of infrared radiation is good for identifying function groups. However, it's also great at warming the planet. The greenhouse effect, right? So, infrared radiation is, I put it so you all know how generally the greenhouse effect works. So you have infrared radiation from the sun that's beamed down to Earth. Some of that is directly, so most of that radiation is absorbed by the Earth's surface and warms it. So some solar radiation is reflected instantly from the clouds or instantly off the Earth. Some solar radiation is reflected in the atmosphere, sorry. Some of that solar radiation is instantly reflected off the atmosphere, and that's usually clouds. Or if you have like the Antarctica has the most amount of infrared radiation that's reflected back, and that's because it has a white surface, if you know about physics. But some of that infrared radiation that is absorbed by the Earth, that is passes through the atmosphere, and some of it is absorbed and re-emitted in all directions. So it's absorbed as high frequency infrared radiation and is emitted as low frequency infrared radiation. That low frequency infrared radiation, because essentially, I'm waffling way too much, but essentially, these greenhouse gases, they can't absorb that high frequency infrared radiation, but when it passes down into Earth and the Earth absorbs it and it re-emits it as low frequency infrared radiation, and that low frequency infrared radiation can be absorbed by the bonds in the greenhouse gases, and then when the greenhouse gases absorb that infrared radiation, they re-emit it in all directions. So back out, some of it goes back out into space, and some of it gets re-emitted back down to Earth. And that's not a bad thing, because that keeps the Earth warm, which is a good thing. But at the rate that we're doing it, humans are doing it, we're constantly putting out these greenhouse gases. That can, too much of that infrared radiation is returning back down to Earth, and that causes global warming. And we already know what the problems are with that. So infrared radiation is useful for helping us to identify compounds because it's absorbed by polar bonds. So we know that on any polar bonds, most of these compounds here, polar bonds, and that's what allows them to be used for greenhouse gases. So molecules in the atmosphere containing the polar bonds also absorb the IR radiation emitted by the Earth. For example, CO2, H2O, methyl groups, CFCs. So it's a water vapor, I should say water vapor, not just water. But once these molecules have absorbed the IR radiation, as I said, they re-radiate it in all directions, including back down to Earth, and this is called the greenhouse effect. Global warming. So the greenhouse effect can be positive, as I said before, because it allows the Earth, it maintains temperatures at Earth, as it helps keep the Earth at a temperature that's suitable for life. But human activities are causing a rise in greenhouse gases, which increase the strength of the greenhouse effect, leading to a rise in global temperatures. Global warming. So with global warming, there's a big threat and can cause extreme weather, which you can see droughts, as you see in Australia, for example, hurricanes, flooding in low-lying areas. I'm not going to go too much into the geography of how floods happen, but you get the point being that the idea that infrared radiation can also cause global warming. The only reason I'm mentioning that, you don't need to know all of this about global warming. You don't need to know. Don't get threatened by the fact that we're talking about global warming, but just know that if they ever give you an example, they might give you an example of, say, one of the uses of, they'll give you like a 6-month question about I don't know, maybe greenhouse gases or polar bonds. You need to understand what is going on. They're not going to ask you about the greenhouse effect, but you need to know of the greenhouse effect, ideally. And if it comes up in the exam, I can say, so and so, greenhouse gases can cause, they absorb the infrared radiation, re-emit it in all directions, and that can lead to the greenhouse effect. And then one of the problems of greenhouse effect, extreme weather, so and so and so. All right, you don't need to copy down all the notes, but just understand what's going on here, and that's it.